for learning. There are 3 students in person. Dylan, Hamza, right?
No, Rob.
Huh? Rob, okay, I'm sorry. Dylan, Rob, and Leslie, these are 3 students, they are attending in person. And we have several online students. Let me see online students, these online guys. Sorry, Sharon. Jake, Justin, Will, and Michael. 4 online students and 3. This is in-person students. I will. I'm going to share my screen with you again, and today I'm going to talk about 2 very, very important examples. So this is examples will appear in our final exam, not will not be included. This midterm almost done, right? So definitely this will not appear in our midterm. However, this will be appearing in our final exam and in the middle of the May. Here are 2 examples I want to illustrate on how to do the tangent calculation for this turning and for this milling. The first example is turning. I want you to know there is a lot of info here, right? First, I want to show you. So this is the typical the 2 pictures. And so first picture and shows that we have a workpiece and we have a tool and we have depth card. This is a depth card. Depth card actually is the difference between the initial diameter and this is the final diameter. So this is called the depth card. Another one is a feed. The feed is parallel to this is the spindle axis, to the spindle axis of this is of this lathe. So in that direction, this is the feed. Another one is the cutting speed. Here, look at here. The cutting speed. So this is the force. So cutting speed, because the spindle, because the workpiece is spinning, the tool remains stationary. So here we will have relative motion between the tool and this is the workpiece. So this is the velocity. This velocity is called cutting speed. Okay, because the relative velocity is called cutting speed. Cutting speed actually is tangential to the outer diameter. It's here. It's going down. So this is cutting speed. So because the cutting speed, we will have 3 forces, and based on that configuration, we will have 3 forces. And first force is that the cutting force FC. It is going down, right? So look at the chip, it's going down. This guy is rotating, and here is the tangential speed. Tangential speed is going down, and here is FC. This is the cutting force. FC means cutting force. In addition to the cutting force, we have 2 other forces. One is in the radial direction. Radial direction is called RFR. Okay, RFR radial direction. This is depth card. This is the radial direction. And MT is called thrust force. Thrust force is along. This is the field direction. This is thrust force. This is called thrust force. Actually, this is thrust force and the cutting force is very, very similar to what we have learned for the orthogonal card, right? So you can see if we take a look at here, and we have a zoom in, and we have zoom in. So here the chip will go this way, and here is the cutting speed, and in this direction will be the thrust force. We have 3 different forces, and these 3 different forces are corresponding to cutting force, corresponding to is the depth card, and corresponding to the feeder rate, or called feed. And feed and feeder rate are the same thing. The same thing. Okay, we know the 3 directions, 3 important parameters: cutting speed, feeder rate, and depth card. And then we will have 3 cutting forces because of Newton's third law. Whenever there is some two objects and they are interacting with each other, If it is an action, we have a reaction. So we have three different forces: cutting force. This is the radial force along with the thrust force. The radial force, as I said, radial force is is along the depth of current direction. Ft is the thrust force is along the feed rate direction. So be very, very careful. So this is very, very commonly seen. These two computers. Also, there's an N here, the capital N. Capital N is a spindle speed. Spindle speed, and for convenience, we for the spindle speed we usually use the RPM. RPM actually RPM is not a standard unit. Okay. RPM means that RPM stands for revolutions per minute. Okay. However, when we calculate, and we usually need to do some conversion from RPM to meter per second. So be very, very careful about that. Then I'm going to give you one example. So this is the material removal rate and cutting force in turning. But the reason I'm going to give you this one is that sometimes when you get your job, okay, this full-time job, when you do something, before you do something, your boss might ask you, "Hey, Rob, this is our configuration. So this is our initial start size, and also what is our final product size. Can you please tell me what is the power consumption on the cutting force and also material removal rate? And even though we just want to have a approximate idea, but can you give me some special idea about this?" And so we do the kind of calculation. So even though we know how to do the modeling, the modeling is much more accurate than this one. But this is empirical based on the empirical equations, and we still can get some sketch idea. This is very, very important, right? So if you can do this one very well, and so you both will have a clear idea and what about the power consumption and the cutting force, the current time material removal rate, and can be expected. So this is, they can just make a final decision about either purchasing this kind of the machine tool or this mobile piece, or they just do something else. So how to do that? Okay, so we have for this case we have a 150 millimeter long. The length is 150. The diameter equals 10. Diameter equals 10. So the 304 stainless steel rod, reduced in dimension in diameter to 8 millimeter. So initial one T0 as T0 is my initial diameter equals 10 millimeter. Okay? So I also know that I want my final diameter. Is the final diameter I know DF. F means the spindle. This equals 8 millimeter. Turning, I ask you to use the turning and use the lathe. And the spindle speed N, and this N equals 400 millimeter. 400 RPM. The tool is traveling at axial speed. Axial speed of 200. This is the millimeter. So this is actually is F. Okay. The traveling. You can see the keyword. The tool is traveling along the spindle axis. So this is the feed rate, axial speed. So F equals 200 millimeter per second, per minute. I'm sorry. So we want to calculate cutting speed, material removal rate, and cutting time, along with the power dissipated, power consumption, and the cutting force. And how to do that, guys? So let's look at, still we need to look at this picture, okay? Look at this picture. This is the volume. So we can calculate, this is the volume, this is a V. Okay, so look at it here. We have D0. With D0 is our initial one. So D0, we have this N here. We have this is N. So D0 equals is a V, the cutting speed, the VC. The cutting speed and the current speed VC. And VC equals what? And VC equals my D0, right? D0 multiplied by 2 pi. I'm sorry, multiplied by pi. D0 multiplied by pi. D0 multiplied by pi equals what? It equals the peripheral length, right? Right? Make sense? I have a circle. If I have a circle, I know the diameter, and pi multiplied by diameter equals the length of the peripheral, right? Okay, so D0 multiplied pi is this is a peripheral length. This is one revolution. But now I know my rotational speed is this. So D0 multiplied by pi, then multiplied by n, right? So one revolution, I have this length. It goes this so far. So the this length is this one. I have 400 RPM. So this equals what? D0 and D0 equals 10 millimeter. D0 equals 10 millimeter. And we have pi here, and we just write D0, and we use the meter. Okay, we need to use it's a 10 millimeter, and we use the meter. The reason is that because the meter is the standard unit for length, and then the n is the 400 revolution per minute. So I will get it here. So remember, so this one will be on 12.57 meter per minute. Pay attention to this. Meter per minute. Okay, so this is my VC. I'm for VC 0 at the very 0. However, the same thing, VC for the F was the final diameter. So then you can see the current speed is a little bit changing. It's changing a little bit, right? Because for turning, because the diameter of your workpiece is decreasing, even though the speed is the same. On VCF and equals pi and df multiplied by the n. So this gives us this is 10.05 meter per minute. So this is my ACF. Did that make sense? Okay, and then we look at the feet. Is the feet. The depth card. We know feet is zero. We know the depth card. The D. And what is the depth card of D here? And depth card equals half D0 multiplied by DF. Why is it half? Because the symmetry we have here and one and another one, right?
Is that a 2 or a wow? What is that?
Huh?
The D, what is it?
2.
Oh, okay. I thought you said something else. My bad.
No. D0 minus DF divided by 2.
I get that, yeah.
Okay, this is the depth card. This depth card gives us, because we have this 10 minus 8 and 2, and here is 1 millimeter. So, so we have this D here. See, I'm calculating this current speed and depth card and also feed. And feed we know, right? This is our feed. See, you got here? The feed is given here. And feed, and this feed needs to be changed. And the feed equals 200 millimeter per second, right? So usually, and this is a feed. This one needs to be changed to revolution. So per minute is 200 divided by 400 equals 0.5 millimeter per revolution. Right? Didn't? You have sense? The feed, and feed, this one is a feed. We know how fast you just want to move the tool along the spindle axis, right? But in order to use the equations we are going to use, so you need to convert this one, the linear speed, and to using this form, revolution. For each revolution, how much you go?
0.5.
Yeah, 0.5. See, mine is 200, 1 minute. My tool goes 200 millimeter, right? 1 minute, see, 1 minute, my spindle spins 400, right? Then I know in each revolution, my tool goes for the 5 millimeter. So because this is a standard unit, is a standard unit for the feed. Each revolution, and you go how much?
0.5.
Yeah, 0.5. Yes. So this, whenever you want to use F and D, and make sure this F is written in millimeter per revolution. So we cannot use this one directly, right? So this is a linear speed, but we need to convert to revolution. Each revolution, and you go how much you go.
So for the millimeters over rev, we would just take F over N, right?
Yes. F over N. F is give you how much you go for 1 minute, and N is how many revolutions I have per minute. And what I want is how much you go per revolution. So this is this one. We need to focus on this. Right?
So that one's just F over N.
Yeah, be very clear. So then I will get this one. We can calculate this MRR. MRR stands for material removal rate. So that means per minute, per second, how much, what is the volume, and you are going to remove. For here, right? For here, how we calculate this one? And because we have diameter D0, also D0, DO, D0, initial diameter, and the final diameter, right? So these two guys are different. Are you agree? The different, we just want to use the average of them. We use a D average, and let me introduce the D average. D average equals and D0 plus DF and divided by 2. Right? Make sense? D average equals D0 plus DF divided by 2. And then MRR can be described using pi D average AVG. Right? Pi multiplied by DVG is the circumferential length, right? Circumferential length, and then multiply by how deep the depth in this direction, right? This direction, this is deep. This direction. So first one, pi d is this direction, then this direction, and then I have another direction, third direction is F. So I have E multiplied by F, then multiplied by my spindle speed. Is how fast I go per minute. right? So you can see, okay? So this is pi d is the circumferential length. So d is the depth in this direction, that is perpendicular to the screen. F is per revolution, okay? See? Per revolution. How much I go per revolution. And then we have this one. So, don't panic. If you don't want to check, if you want to use this one, it's still okay. But if you use 200 directly, and you will not multiply by n here again. Make sense?
Because it cancels it out, right?
Yeah. So actually, this f multiplied by n actually is 1 minute. 1 minute, how long you go? Actually, it's 200. But like mentioned, we use the f, and we use this one to denote f for the unit as f. So pi d f, this is the volume per revolution. Then multiply by how many revolutions per minute? That means volume per minute, right? So you just plug in, and you can just plug in, you will get this 56 and 55 millimeter per minute. So this is the MRR. And then we look at this is the cutting time, T. The cutting time T, and T equals the length. The length divided by F multiplied by N. Right? Actually, this how fast you go, right? So this is very easy. Okay, length is 100. This is Fn, F is 0.5 multiplied by N 400. So actually, this one equals 200, right? So this gives us 0.75. You understand? Actually, this is linear. 1 minute I go this one, but I totally want to go 150. The average is 150 divided by 200. Right? Oh.
Where's 150?
Huh?
What is, the length.
150? Yeah, 150 is given. Given. My bar is 150 meter long, millimeter long. 150 is given. You have sense? Okay, then we calculate this specific energy. We have specific energy. And specific energy for the 304 steel and stainless steel, and we can just select 4.1 volts second and millimeter cubic. And then we can calculate the power. The power so equals, and this is the specific energy 4.1 multiplied by this. 4.1 multiplied by 5655. So remember, here is a minute, okay? So because here's a second, here is a second, okay? But here is a minute, and you need to divide by 60. So for 60 seconds, I have this. For 1 second, definitely this guy divided by 60. Right? and then multiply by this one. This will give us the 386 watts. Watts is an energy per unit time, right? Per second, to be specific. Question so far? No question? And we have, and we will get power, and we can calculate, and we get power, we can calculate the T. The FC, we calculate the FC. FC is a tangential force. T, the power is the product of the torque and the rotational speed. So, is the power equals, right? Is the power equals the torque multiplied by rotational speed. This is rotational speed is omega. Is the torque. This is rotational speed. So we can have, so based on this one, the torque equals the P divided by omega. What is omega? Here, 400 RPM. Right? So P we see, but pay attention to the unit. And 386 watts. W, omega equals N. I'm sorry, we'll see. Omega equals N. Omega is omega equals N. Here. So omega equals N 400 RPM, right? RPM per revolution, and we need to change to the standard unit. Our revolution is pi. I'm sorry, the 2 pi, one revolution is 2 pi. 2 pi divided by 60. So this one I will change to radian per second. So this W needs to have radian per second. How to change from 400 RPM to radian per second? We have 2 pi, 1 pi, 2 pi, right? Because one revolution is 2 pi. 1 minute is 60 divided by 60. Right? And so based on this one, we can calculate this equals 9.2 Newton meter. 8 Newton meter. FC, this is T equals Newton meter. So MC equals the torque divided by D average. I'm sorry, D average divided by 2. Does it? The torque, we know the torque. We know the torque, right? So we know the force. Force is equal to this direction. The force multiplied by the radius. Torque multiplied, force multiplied radius equal torque, right? This radius equals half the average divided by 2. So this gives us the 2.0 kilonewton. Just plug in. Any questions so far? So let me summarize this one a little bit. So you already have initial diameter, final diameter. Always N is given as RPM. Be very, very careful. RPM is very, very convenient, but when we calculate, we need to pay attention to the conversion. F given as a millimeter per minute. Okay, so this can need to be changed to millimeter per revolution. So also pay attention to the how to calculate the depth card. Also how to calculate this is the D average. Let me write down D average equals D0 plus DI. IMRR, current time, and the specific energy was already given, and the specific the power equals the torque multiplied by the signal speed. And then based on T, we can calculate the current speed. Any questions? If no question, we move on to the next one. Next one is the medium, is the phase medium. And phase medium, let me take a picture. So this is a phase medium, and for the phase medium, we have this is this diagram, and phase medium, the workpiece is moving, translational, is translating. This is this guy is moving also here, right? This is rotating, and by the V, the workpiece is translating. So we want to calculate the so-called things. On first one, we want to calculate MRR, material removal rate, and we also want to calculate the current time. For our case, so this is D 150. This is omega. Omega is this W, so we call W. From the center and to this edge is 60 millimeter. L is the length of the workpiece, equals 500 millimeter. D is given, and D is a depth card, and D is depth card. Here is given. V equals 0.6 millimeter, and is a translational velocity, and N is the spindle speed, and for your cutter, the cutter is the cutter has 10 inserts. Okay, it's a very big one. Let's say big one has 10 inserts. The workpiece material is high strength aluminum alloy, and we are asked to calculate the material removal rate, current speed, and feed tools, and estimate the power consumption. Okay, here, okay, so this figure, this is the cutter, and this is F is feed rate usually per revolution. So here we are going to solve the problem. Let's solve the problem. The cross sectional of the cutter, equals W. This is a W is 60 millimeter cross section here. W multiplied by the D, the depth, right? The depth here. D, this is W multiplied by the depth here. This is W multiplied by the D. The cross section. The cross section equals, this is the W multiplied by D. W is this way, this is the D, okay? The W multiplied by D is the cross section. It equals 60 multiplied by 3, and we can get 180 meter. So this is the cross section. The workpiece is V, right? So the V equals the V is there, and V equals 0.6 meter per minute. So this one can be changed to minute, right? So also change to millimeter. So 600 millimeter per minute. So the material removal rate equals what? What guys? So this is my W. This is my D. Right? Then this is my velocity. Material removal rate is volume per unit time. Yeah. Okay?
Yeah, okay.
So think about it. Okay? This is my W in this direction, right? So here is my D. W multiplied by D is the area. This is my area. But I also know the velocity, how fast this guy goes in this direction, and in the third direction. If I multiply them together, that will be the volume per unit time. MRR. So that means the MRR equals my W, right? Multiplied by D, then multiplied by V. So this one can be obtained as 180 multiplied by 600. So millimeter cubic per minute. Be very, very careful. Here is a millimeter. That's the reason we need to have millimeter here as well. Right? Because these are three dimensions. When you multiply them together, these three guys are supposed to have the same unit. Right? Okay, so this is my MRR and the cutting speed, the cutting time. And look at the cutting time. The cutting time here, the cutting time equals, so this is my speed, okay? So this is my speed. Cutting time equals L distance multiplied by plus this one and plus this one and divided by the velocity. And T equals L, the length of your workpiece, and plus 2 multiplied by LC. LC is before this tool, this cutter, before this cutter enters this guy. I'm sorry, here is enter. This guy enters. So you can just assume this work for this case, workpiece remains stationary. But my cutter is moving, okay? So this is my cutter. At the very beginning, my cutter is here, then goes through until my cutter leaves, disengage, until my cutter disengages with the tool, with the workpiece, I'm sorry. That makes sense?
Mm-hmm.
Relative motion between workpiece and the tool. So here, so this is divided by velocity. I'm using the symbol, using the same thing. So T plus T is 2LC. Now, and how to calculate the LC? How to calculate the LC? Here is the LC. Right? This is very, very important. Here is LC. This is LC. If I draw, this is my LC. If I draw here, okay, let me draw. I cannot draw here. Okay. So you can see from here. So you can see this for this distance. The center is to the left of this is the left edge, right?
Mm-hmm.
So I know that here, if I draw the line from this point corner to my center at this distance, I can draw a line, right?
Yeah.
Do you agree? Then from here to here, this equals my LC. Okay, the center is LC. So this is my D, this is my LC. LC means the distance of your center when this one is disengages with your own piece. So this is my D. So when I know this size is LC,
So this is my D, okay? This is my D. And here is my LC. Right? But here is my right angle. You understand? Okay, my D is known.
And the right angle is along the center? the
Yes.
center line?
Go here, from here to here. I cannot.
Yeah, you kind of did that, you kind of did that in reverse when you initially showed it, but yeah, this makes sense.
Here is the D, here is this hypotenuse. Here's the hypotenuse. And here is the vertical line, which is equals LC. And here, this one. So in order to calculate this one, I need to calculate this, right? And how to calculate this? See, you can see, this is my center, this is my center, right? My center equals, what is my center? What is this? This one equals half D minus the W. So this guy equals half D minus the W. Right?
Mhm.
So because I know this is a right triangle, I can use the Pythagorean theorem. So as a result, and so this equation holds. So LC square plus E over 2 minus W. So this guy equals the square of the hypotenuse. The hypotenuse equals half B. I'm sorry, here's the half D, I'm sorry. Here's the half D. Okay? Because it's from here to here. The half D, not the total D.
So half, so D being the diameter, so just be the diameter of the two, right?
Radius, yeah, radius from here to this point.
Yeah.
Yeah, then, so the D is given, W is given, and one equation, and I can calculate this LC. LC, you can calculate this LC as 73.5 millimeter. Right? Then after you get this LC, you just plug in, and then you can calculate the T. And T, and you can calculate L is 500, L is L is 500, 500 and plus 2 LC, and divided by visual length, and divided by the 3 is 600. You know, this is a millimeter, okay? This is a, I'm sorry, this is a minute. And this is a minute. So this is the length, and this will be the minute. And this one will be the minute. This is a minute. If this is a minute, and you need to change to a second. So here it equals 1.08 minute. Or you can change to second. If you can change to second, it equals 6.7 seconds. This is T. And then we look at this is the feed rate. Is a feed. And the feed. Oh, okay, sorry. Let me finish. The feed rate, feed equals the velocity and multiplied by n. And this is n. Right? So V we have here. So this n is the number of inserts, number of teeth. And so this capital N is the spindle speed. Spindle speed. So as a result, RF equals V N capital N lowercase n. So here we will have, I'm sorry, I'm going to finish very quickly. So here is a 10. So this is V, okay? So our n equals 100 RPM. 100 RPM equals 1.67 revolution per second. So make sure this V is the minute per second, millimeter per second. So here is for the 6 millimeter, 600 millimeter, it equals 10 millimeter per second. Right? So be very, very careful. If you want to divide something, you must unify the units. So this V, my V here is 10 millimeter per second. My N is 1.67 revolution per second. My N is 10, okay? I have 10 teeth. See? I have 10 teeth, 10 inserts. So for this one, and the results will be millimeter per revolution. Because our F is usually millimeter per revolution. So that's the reason we can get here. So here is 0.6 millimeter. Okay, per teeth, right? Per teeth. Revolution, in one revolution, we have 10 teeth, right? So that's the reason the 0.6 millimeter per teeth. Per tooth, no, I'm sorry, not per teeth. If you per, you cannot tooth, right? Plural form. A singular form. Tooth. And then the power, and you can calculate the power. And power equals the specific energy is a specific energy. I'm sorry, guys. I'm going to finish very, very quickly. I multiply by MRR. MRR is this. And it gives us 1980 is the watts. 1.98 kilowatts. Right? So, two important points. Here, how to calculate this LC and use that diagram. You use that the right triangle. So, second, and how to calculate this F. But for the meaning, we